Hello again. This is Math 1115, Alternative Delivery, and we're covering 5.2 content. Do make sure, I want to start by reminding you that this is your opportunity to make some magic today. I'm encouraging you to stay the course. I think those that stay can be champions. Teaching and learning is possible. Grades will be earned and rendered, and your educational goals need not be deferred. Today we talk about linear equations and simultaneous linear equations, multiple linear equations. So two linear equations, each contain the same unknowns. So we have x and y are the unknowns on these equations, and the a's, b's, and c's are all constants, are said to form a system of linear equations and two unknowns. A solution of the system is a pair of numbers, x, y, that makes both equations true. Except in special circumstances, and we will talk about those later, there will be only one pair of numbers that make both equations true. That's because fundamentally you can say two lines intersect in a point. And we do a couple of examples, and as John suggested, I'm going through some of the examples in your book in these new videos. So, here we have two equations and two unknowns up here. And the question is x equal 2 and y equal 8 a solution of this system? Well, we plug them into both the top equation. On the top equation, when we plug x equal 2 and y equal 8 on this side, we get 18. That matches. And when we plug x equal 2 and y equal 8 into the second equation, that also matches. So since both the equations are true, x equal 2 and y equal 8 is a solution to the system. Now, these problems are very applied, and so you can have a situation where you are dealing with forces, and here are two equations and two unknowns. The two unknowns are F1 and F2, F1 and F2. And so the question is F1 equal 18 and F2 equal 41 solutions to this system of equations? Well, we have to test both of them. When we plug into the first equation, we find out that it does work, but when we plug it into the second equation, we find it does not work. So since one of the equations is not true, that is not a solution to the system. We try then to find the points of intersection, and the way we try that is by graphing the two lines. So here we'll graph y equal x minus 3 and y equal minus 2x plus 1. And we will try to, we will graph both of those. The first one has a positive slope, the second one has a negative slope. And so you see here are the graphs of these. Now we learned how to graph these in the last section, so you should be good with that. Now what really happens though is when we look at the picture we say yes, they do intersect at a point, but it's difficult to tell from the graph what is the real point of intersection. And we guess based on the accuracy of our graph in this chapter. In the next chapter we're going to learn how to solve these exactly, which will be a lot of the focus of what we do. But here we get 1.3 and minus 1.7 is our guesses. Now the exact solution isn't that. This is going to be the exact solution, but those are sort of close. These are approximate solutions. Your textbook spent some time going over calculator solutions. The calculators that we use in this course, I'm not trying to make you buy expensive calculators, will not do this, but others will, and maybe someday you will spend that money on the calculator to get approximate solutions. Here's another example. We're graphing this differently though. Here we probably would graph these by the technique of finding the x and the y intercepts. And we draw both lines in this case. So here's two equations and two unknowns. One of the things I think you should maybe note is that the x's are over the x's, the y's are over the y's, and the constants are over the constants. So when I look at the imaginary line that I'm drawing right now, this ratio is 2/3, that ratio is -5. That means the two lines have different slopes, and that means that they will intersect in a point. When we look at the graphs up here, we see that the approximate point of intersection looks like 2.3 and 1.2. We check it, and it is an approximate solution. Not exact, but approximate. Now this is one of the kinds of special systems that we have. And this is called an inconsistent system, and this is what happens when the two lines are parallel. Now if we look at these two lines and if we graph them, we would see that, oh yeah, they're parallel lines. They both have the same slopes, 1/2, and they have different y-intercepts. And so that's what we get when we do this kind of work here. So they don't intersect, and that means that there is no solution. And we call such a system inconsistent. Now, outside of a math class, if you encounter an inconsistent system, the no solution means, if you didn't make a mistake, that means you were given an impossible task. And you would appeal to your management about this. You would not think that this happens, but it really does. Often people are assigned impossible tasks. The other type special system is called a dependent system. Now if you look at this, I have the x's over the x's and the y's over the y's and the constants over the constants. Look here, when I do this, what will happen is the ratio of the coefficients would be -1/2. The ratio of the coefficients here are -1/2. That means these two lines do have the same slope, but over here is also -1/2. That means they're the same line, exactly the same line. So both equations fall on top of each other. There are an infinite number of solutions, and such a system is called dependent. Now outside of a math class, if you encounter a dependent system, that usually means you committed a modeling error. Let's look at some examples. Life is a word problem, so I'm choosing to look at word problems here. And these are very real problems if you're dealing with mechanical engineering or mechanical technology problems. You might be dealing with tensions. And so there's a tension 1 and a tension 2 here. And what we can do when we study these is that we can formulate some conditions for equilibrium so that this mass is not going back and forth and also not falling down. So what is up the vector sum of what is up has to be the same as the vector sum of what is down, and the left and right components must also be equal. If you turn those into equations, you get these two equations and two unknowns. I'm going to ask you to press pause, work the problem, find out where you think these T1 and T2 are, and again we're doing it approximately, and then hit play. Let's see how you do. Let's see how you do. Well, when you graph these, what you will get is a graph that looks like this. This is the, and what I'm doing is I'm taking T1 to be down here and T2 up here. So I graph the two lines, and what I will get is it looks like it's something around 50 and around 47, and so that's in fact what I'm going to round them off to. These are not, well actually these end up being pretty much exact answers that we can get for this, but that's the way that we can follow on this. Here's another problem. It's a word problem, and an architect is planning a parking lot. He's got 202 feet wide, and he's dividing spaces for compact and full-size cars, and he wants 16 of these, 6 of those that will use the space completely, or 12 spaces and 9 spaces, and 1 will be left over to use the entire space. So what are the widths of the spaces that he's planning? So hit pause and think about the problem. I'll return and we'll see how you did. Let's see how you did. And so we let X be the compact car width and Y be the full-size car width. And so then what we get is, this is the first equation. This is the second equation. We graph both of those equations on the same axis, and we see it intersects about at 8.5 and 11. It turns out this is exactly, and so that means that the compact width is 8.5 feet and the full-size car is 11 feet in width. The last problem, and this also applies to electrical technologies, electronics technologies, and it is derived from using Ohm's law and also Kirchhoff's law, you can come up with this set of equations, and these are the currents I1 and I2 that are going through this circuit. Okay, I2 is what is going through the bottom piece here, and I1 is what's going through the top piece here. And so we end up with these two equations and two unknowns. The variables are I1 and I2. So I'm going to ask you to hit pause, try to work the problem, and come back and we'll compare notes. Press pause now. Let's see how you did. Okay, so the first equation is up here, which simplifies to 8I1 plus 6I2 equal 12. So we graph that. For the next equation, what will happen is that will simplify to 6I1 plus 10I2 equal 12. So we graph those two equations and we see that's about where they intersect. And so the solution is approximately 1.1 and 0.5. Again, we'll talk about how to solve these exactly in another video very soon. So now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. Take care.